Hi, welcome. My name is Alfonso Nava and I'm going to talk about asteroids. We all have heard how an asteroid could kill us, and every year we read some kind of fake news about how an asteroid flies few meters from Earth or is going to hit us soon. To have a better understanding about these astronomical bodies and how does their cycles and orbits work, we will do an experiment regarding these two terms, and based in the law of universal gravitation and our imagination and logic, we will understand this by doing an experiment and analyzing their orbits and cycles around the Sun. Theory. As you may know, everything on Earth is pulled downwards by a force called gravity. It is the attraction force between two objects with certain mass, but gravity is not an Earth-only phenomenon. Long time ago, a scientific named Isaac Newton said that gravity was universal. This means that it exists everywhere in our universe, and that's why it affects our asteroids that we're studying in our solar system. The law of universal gravitation states that the force of gravitational attraction is directly dependent upon the masses of both objects and inversely proportional to the square of the distance between their centers. This meaning that the longer the distance, the less the gravity will affect. Now, there are three different types of asteroids. The first one, the C-type, add up to 75% of all asteroids. They are known as carbonaceous because they contain carbon compounds and they are basically made of clay and rocks, and sometimes can contain large amounts of water in different forms. The second one, the S-type, silicaceous or stony asteroids, represent 17% of asteroid population and are made of stony materials, also known as silicates, from here the name, and they can also contain nickel, iron, and in some cases contain precious metals like platinum. And the third and last one, the M-type, are metallic form asteroids. As the name says, these asteroids contain very high quantities of metallic materials. Now their orbits. The orbit of an asteroid is divided in different parts. For example, the semi-major axis. It is the distance equals to the half of the major axis of the ellipse. The major axis passes through the center of an ellipse and ends in the widest points. It is measured in astronomical units. One astronomical unit is equal to the Earth's average distance from the Sun. The perihelion, that is the object's closest distance to the Sun. The aphelion, that is the object's farthest distance from the Sun. The eccentricity, that measures how circular an orbit is and has a value from 0 to 1. And an orbital period, that describes how long it takes an asteroid to orbit the Sun once. Orbital period is measured in years. Methodology. Our research question is, how does the mass of an asteroid affect its orbital period? This leads us to our hypothesis. According to the universal gravitation law, the bigger the mass an object has, the bigger the gravitational attraction between this object and other mass will be. So, the bigger the asteroid it is, it will go faster because of the attraction with the Sun. Our variables are independent, that is the mass of the asteroid, dependent, the time it takes to complete a lap to its orbit, and controlled, the size and the shape of the orbit, or the distance it will cover. The steps to follow are the next. First, select the asteroid with a similar orbit size in the database. In the database, select as in the first image to your right. This will limit the data we'll be getting and record to our variables. In the step 2, 3 and 4, just click the pen select option and remove all the variables except the circle in the orange, that are GM, A in astronomical units, object full name, and period in years. Now step 2, analyze the changes in the orbital period. Step 3 is verify the data used is correct and the mass of the asteroids is different. And number 4, watch the results in Excel page so they are ready to analyze them. Now that you have your results, you gotta analyze them, and after that you gotta make a table to make sure you have no mistakes. For example, in the GM, the standard gravitational parameter that measures mass, all the asteroids have to have a different mass. The orbital period has to be not that different, but it has to be a little bit different, and the size of the semi-major axis gotta be the same or almost the same for all of them, so the time doesn't vary a lot, and you can make sure you can analyze the speed of each asteroid depending on its mass. In the next graph, you can watch our results. The biggest difference I can see is in the mass. For example, from number 1, that's 1 series, to number 5, that is 253 material. In spite of the mass difference, the orbital period does not vary a lot. It does have its variations between the asteroids, but it wouldn't be as big as I expected. And we made sure that the size of the semi-major axis will be the same for all of them. It also varies a little bit, but we wouldn't express it in here. And to your right you can see the two Pallas orbits compared to the Earth's, Mars, Mercury and Venus orbits. And last but not least, the conclusion. As we can see in the results, our hypothesis is right, but only partly. Sadly, there are other variables in our solar system that we can control, and these variables affecting a big scale or experiment. That's why I chose asteroids that had the most similar semi-major axis, so this way at least two of them could be similar results. It's funny how the smallest of them is the one that goes faster, but we can also observe that it's the one that has the smallest orbit. And we're not taking into account other factors as previous impacts that gave them speed, or the number of obstacles or impacts they go through when orbiting the Sun. Anyways, thank you for being here, and I hope you have a nice day.